Okay, so in this video we're going to explore some different types of forces, and we're going to start making something we call a free body diagram, which is a diagram essentially in which you draw the forces acting on something. Okay, so the way that we're going to go about doing this is by drawing some different situations and then analyzing them to think about what forces are involved. Okay, and so for the first couple of videos, we're going to just focus on scenarios where the forces are balanced, where an object is in equilibrium. In those circumstances, what can we say about the motion of an object? Okay, so to continue, let's say that we have a block, and to start I'm going to tell you what the weight of the objects are. In a couple days I won't tell you what their weight are, I'm going to have you figure that out. So this object has a weight. The unit we use for force is newtons, okay? So we're going to say this object has a weight of 10 newtons. And let's say that it's sliding across ice at a speed of 3 meters per second. Okay? Well, we want to diagram the forces here. Okay? We know the forces are balanced because it's moving at a constant speed. Okay? And so we know that there is a downward force because of the weight. Okay. And so weight occurs whenever you have something close to the surface of the earth. So when something is close to Earth's surface. Okay. And it always happens, you always have weight when you're close to Earth's surface. Okay, and it doesn't have to be Earth. So whenever you're close to like a planet's surface, so you could have weight on the moon, you could have weight on Mars, you could have weight on the sun in the instant before you were incinerated, you could have weight on Pluto. Okay, so anyway. But weight comes from being close to that surface. Gravity doesn't just act close to Earth's surface, but we kind of think about it differently when we're not close to Earth's surface, okay? So weight is when something is close to Earth's surface. And if we were just to have this diagram here, this looks unbalanced to me. I have a pull downward. There's nothing pulling the other way. And so if there's a pull downward with nothing pulling back, that means that velocity is going to change, so it would be falling downward. We know that's not the case. We know it's sliding along, so there has to be something balancing it out. Okay, which means that there is an upward force, this one from the ground, pushing back up on the object. Okay, and so this earth, or this weight came from the earth, acting on the box. Okay. And so it's nice to label the forces where they came from. And then we have this upward normal force. That's what we call the force from a surface. So the upward normal force from the ground on the box. Okay? And so a normal force occurs whenever surfaces are in contact. Okay? Sorry, I'm struggling with writing today. So normal force occurs when two objects are in contact. Okay. Alright, and so we can say how strong these forces are. We know the weight of the earth, or the weight of the box from the earth, is 10 newtons. And so we can say, well, the normal force on the box from the ground must also be 10 newtons in order to balance it out. Okay? If this upward force was less than 10 newtons, then this box would accelerate downward. If this upward force was greater than 10 newtons, this box would accelerate upward. Okay, since neither of those things are happening, then we know that those are the same. Okay? And the next question is, should we put a force this way since the object is moving to the right? The answer is no. According to Newton's first law, this object will keep going to the right forever unless there's a force causing it to slow down. Okay, and so in this case, if this is some frictionless surface, which we'll have to assume, then this object is able to slide like this forever. Okay, and so that is our first free body diagram. Okay, now we're going to do another one. We have a similar box. This time it's being pushed at a speed of 3 meters per second. Still has a weight of 10 newtons. But now, in order to push it, we're required to push with a force of 5 newtons. Okay, so to draw this diagram, we say that, okay, that we have some amount of weight, right? That's the same. The weight hasn't changed. This is from the earth on the box. We have an upward normal force from the ground on the box. Those are things are still happening because we haven't done anything to affect them. Still weighs 10 newtons. Okay. And then we have now a push this way of 5 newtons, and we'll call this an applied force. Okay, so an applied force would be when something applies a force to an object. Okay, but we know that the speed of this object isn't changing. It's going at a constant speed, which means the forces have to be balanced. So for it to push that way with 5 newtons, something's going to have to push back with 5 newtons. Okay, and so in this case, the thing pushing back is friction. Okay, and it turns out there's two kinds of friction. This kind would be called kinetic friction. Okay, so the next force that I want to talk about is kinetic friction. So kinetic friction occurs when a surface is sliding across another surface. When a surface slides on another surface and it's opposite the direction of motion. I'm sure you can read this. Sorry that it's so messy. Okay, and so that's kinetic friction. So we have a similar situation here, except since friction was present, in order to push at a constant speed, we now had to push with 5 newtons of force. Okay, so here's another scenario I want to look at. We have a book that weighs 15 newtons, and we're pushing on it. Okay, we're pushing it into this wall, and it's being held in place. It's not sliding down the wall. Okay, it's just kind of sitting there against the wall as we push against it, okay? And so we're going to draw a free body diagram for this one. Okay, so what would be this downward force right here? This would be the weight from the earth on the book. That would be equal to the weight of 15 newtons. Okay, let's say that we're pushing on it with 25 newtons of force. So we're pushing this way with a force of, we'll say this is an applied force of 25 newtons. Okay, and then we know that it's balanced because it's not moving, which means we need to balance out this force, and we need to balance out this force. Okay, so let's start with this one right here. What force do you think is pushing out of the wall to balance this out? What would we call that force, and how strong would it be? Well, this would be a normal force because that wall is in contact with the book. So from the wall on the book, and this would be equal to about 25 newtons to balance out that other force. Okay, and then what kind of force do you think is pushing up right here, and how strong do you think that is? Well, this is going to be friction, okay, but this is a different kind of friction than before. Okay, this is called static friction. Okay, kinetic friction, remember, it was when surfaces are sliding across each other. Okay, static friction here is the friction required to hold it in place. Okay, and so this is from, again, the wall on the book, and it's going to be equal to, again, 15 newtons to balance out that weight. And so it's at rest here, okay, which is an example of something that's at a constant velocity. Okay, so the new kind of force we introduced here is static friction. Okay, and static friction is force required to keep something from sliding. Okay, and its direction, I can't edit that. Right, its direction is going to be opposite whatever force it's balancing out. Okay, and so that's static friction. And then there's one other kind of force I want to mention before we wrap up this video. Okay, and so let's say that we are walking along, pulling some kind of cart. Okay, and let's say that this cart has a weight of, let's say 30 newtons. Okay, and let's say that we're standing here and we're pulling it with a rope. Okay, and let's say we're pulling it with a force of 6 newtons. Okay, and so if we want to draw a free body diagram for this, well, we're going to have the downward weight from the earth on the cart equal to 30 newtons. We're going to have an upward force of what with how much strength? A normal force with 30 newtons. Okay, then we have the force from the pull. So if we're pulling with like a cable or something, we can call this tension, and we'll call it tension from the rope on the cart, and that's equal to 6 newtons. And then finally back this way, we have something's got to be balancing this out, and so we're going to call this friction from the ground on the cart, and that's equal to 6 newtons. Now it's moving, so you might think kinetic friction, but actually technically this is static friction because the wheels are what's in contact with the ground, and the wheels aren't sliding. At the moment they're at the place where they're in contact, they're actually at rest. So we'll just put friction, just because we'll get into a little bit deeper into that rotation stuff next semester, and this concept of friction there, or static friction there. But so we'll just say friction, but just technically it's kinetic or static because it's not sliding. Okay, so this last force is tension, and tension is just the force that is carried through like a cable or a rope. Okay. We'll say a force applied through like a cable or a rope. Okay, and so these are the kind of forces we're going to start out with. There are other forces that exist. Okay, I'm sure you could think of some, but some we'll get to later, and some we unfortunately won't be able to discuss this year.